Memory is one important and crucial resource on our machine, and it is always good to know the architecture of memory, the way operating system manages memory, and the way memory is accessible to us as programmers. In this lesson we will discuss the concept of dynamic memory, and we will see how to work with dynamic memory using C or C++. The memory that is assigned to a program or application in a typical architecture can be divided into 4 segments. One segment of the memory is assigned to store the instructions that need to be executed. Another section stores all the static or global variables, the variables that are not declared inside a function and that have the whole lifetime of an application. They are accessible anywhere during the whole life cycle of the application as long as the application is running. One section of the memory is used to store all the information of function calls and all the local variables. And we have also talked about stack in our lesson on call by reference. Local variables are declared inside a function and they live only till the time the function is executing. The amount of memory set aside for these 3 segments, the text segment, the global variable segment, and the stack, does not grow while the application is running. We will come back to why we use this 4th segment, heap, in a while. Let us first understand how these 3 segments of the memory are used when a program executes. I have a simple C program here. We have a function square that gives me the square of a number. We have another function square of sum that is given 2 arguments x and y, and it returns us the square of x plus y. And in the main method I'm just calling this function square of sum, passing it 2 arguments a and b. Let us now see what happens in the memory when this program executes. Let us say this rectangle in green here is memory reserved as stack, and this rectangle in orange is the memory reserved as static or global variable section. When the program starts executing, first the main method is invoked. When the main method is invoked, some amount of memory from the stack is allocated for execution of main, and this total is a global variable, so it should sit in this section. The amount of memory allocated on stack for execution of main can also be called the stack frame for the method main. All the local variables, arguments, and the information where this function should return back to, all this information is stored within this stack frame. The size of the stack frame for a method is calculated when the program is compiling. Now when main calls square of sum method, let's write shortcut SOS for square of sum, then a stack frame is allocated for the call to square of sum. All these local variables x, y, z will sit in this particular stack frame. Now sum of square calls square. Let's again put a shortcut here for square. So another stack frame for square, and it will have its own local variables. At any time during the execution of the program, the function at the top of the stack is executing and rest are kind of paused, waiting for the function above to return something, and then it will resume execution. I have drawn these play and pause button here in case you do not understand. Okay, so this total is a global variable. It sits here in this section. Global variable because it is not declared inside a function. We can access it anywhere. And then we go to this particular statement where we call square of sum, and square of sum is calling square. So right now this is our call stack. This program may not be the best way to implement this logic. I have written this program this way so that I can have some nested methods calling each other. Let's say right now we are at this particular statement, we are executing this statement. So at this stage call stack will have these 3 methods. Now when this method finishes, we will return back to this particular statement. As soon as square function will return, it will be cleared from the stack memory, and now some square of sum function will resume. Once again, when square of sum finishes, the control will come back to this particular line. Line total is equal to square of sum, and main will resume again. Now main will call printf. So once again printf will go to the top of the stack, printf will finish, and the control will come back again to main, and now main will finish. And when main finishes, program will also finish. So in the end our global variables will also get cleared. There was no need in this program to keep this variable total as global. We should assign a variable as global only if it is needed at multiple places in multiple functions, and it is needed for the whole lifetime of the program. Otherwise it's a waste of memory to keep a variable for the whole lifetime of program execution. We had kept one global variable in this program just to understand the concepts. Here I must point out one more thing. When our program starts, our operating system allocates some amount of reserved space. Let's say OS allocates 1 MB of space as stack, but the actual allocation of the stack frame and the actual allocation of the local variables happens from this stack during runtime. And if our call stack grows beyond the reserved memory for the stack, like for example if a method A calls B, B calls C, and we go on calling and we exhaust the whole space reserved for the stack, then this is called stack overflow, and in this case our program will crash. One common case of stack overflow is when you write a bad recursion and your program goes infinitely into recursion. So as we can see, there are some limitations of stack. The memory set aside for stack does not grow during runtime. Application cannot request more memory for stack. So if it is 1 MB, then if the allocation of variables and functions in stack exceeds 1 MB, our program will crash. Further, the allocation and deallocation of memory onto the stack happens by a set rule. When a function is called, it is pushed onto the stack on top of the stack. When it finishes, it is popped or removed from the stack. It is not possible to manipulate the scope of a variable if it is on the stack. Another limitation is that if we need to declare a large data type like an array as local variable, then we need to know the size of the array at compile time only. If we have a scenario like we want to decide how large the array will be based on some parameter during runtime, then it is a problem with stack. For all these requirements, like allocating large chunks of memory or keeping a variable in the memory till the time we want, we have heap. Unlike stack, application's heap is not fixed. Its size can vary during the lifetime of the application, and there is no set rule for allocation and deallocation of memory. A programmer can totally control how much memory to use from the heap, till what time to keep the data in the memory during the application's lifetime, and heap can grow as long as you do not run out of memory on the system itself. That is a dangerous thing also, and we need to be really careful about using heap for this reason. We also sometimes call heap free pool of memory or free store of memory. We can get as much as we want from the heap. How heap is implemented by the operating system, language runtime, or the compiler is something which can vary, which is a thing of computer architecture. But an abstracted way of looking at the heap as a programmer is that this is one large free pool of memory available to us that we can use flexibly as per our need. Heap is also called dynamic memory, and using the heap is referred to as dynamic memory allocation. And let us now see how to use the heap in our C or C++ program. I will clear this code in the left, and I will draw one more rectangular block here for heap. There is one more thing that I must point out before moving forward. Heap is also one data structure, and if you do not know about this data structure heap yet, you will learn about it in your data structure course. But this nomenclature here has nothing to do with the heap data structure. The term heap here is being used only for the large free pool of memory. Heap data structure does not come anywhere in this context. This term often confuses a lot of people when they know about heap data structure. Stack is also one data structure, but the stack segment of the memory is actually an implementation of stack data structure. but heap is not an implementation of heap data structure. To use dynamic memory in C, we need to know about 4 functions: malloc, calloc, realloc, and free. To use dynamic memory in C++, we need to know about 2 operators: new and delete. These 4 functions can also be used in C++ because C++ has backward compatibility. It is only a superset of C, but C++ programmers mostly use these 2 operators, new and delete. We will see some code examples and try to understand how things happen when dynamic memory is used. Let us first pick up some code example in C. Let us write a C program. I'll clean up some of this stuff in the right. 1 MB for stack, this was just an assumption. In reality, the size of the stack will be decided by the operating system and the compiler. It is a thing of architecture. Coming back to the code, if we declare a variable like this, then this variable is a local variable. It goes on the stack. Memory for this particular variable A will be allocated from the stack frame of the main method. Let us say we want to store an integer on the heap. To reserve or get some space allocated on the heap, we need to call the malloc function, something like this. The malloc function asks for how much memory to allocate on the heap in bytes. When we say malloc and pass as argument size of integer, then we are saying that, hey, give me a block of memory which is 4 bytes. 4 bytes is the typical size of an integer. So one block of 4 bytes will be reserved or allocated on the heap, and malloc will return a pointer to the starting address of this block, and malloc returns a void pointer. Let us say the starting address of this block of 4 bytes is 200. So malloc will return us the address 200. Now we have a pointer to integer p, which is a local variable to main. So this will be allocated in the stack frame of the main method. We have done a typecasting here because malloc returns pointer to void pointer, and p is an integer pointer. Now p stores the address of this block of memory, which is 200. So we have got some block of memory on the heap which we want to use to store an integer. Right now we do not know what's there in this particular block of memory. If we want to fill in something here, we need to dereference this location using the pointer p and then put in some value. In fact, the only way to use memory on heap is through reference. All the malloc function does is looks for some free space in the heap, books it or reserves it for you, and give back the pointer. And the only way you can access this particular block by keeping a pointer variable which will be local to your function. Now let us write something like this. After writing 10 in this particular block, I will go ahead and make one more call to malloc. When I make one more call to malloc, one more block of 4 bytes is allocated on the heap. Let us say the address is 400 for this block. Now the address that is returned by this second call to malloc, we store this address in the variable p. So what happens is that p is now pointing to the address 400. The next line writes 20 at this address. We allocated one more block and we modified the address in p to point to this block. The previous block will still sit in the heap. This memory we are still consuming. It will not be cleared off automatically. At any point in our program, if we are done using some particular block of memory which is dynamically allocated using malloc, we also need to clear it because it is unnecessary consumption of memory, which is an important resource. So what we should have done here is that once we were done using this particular block of memory at 200, we should have made a call to the function free. Any memory which is allocated using malloc is cleared off by calling free, and to free we pass the pointer to the starting address of the memory block. So now with this code, this first block of memory will first be cleared and then we will be pointing to another memory address. It is the responsibility of the programmer to clear anything on the heap if he has allocated it and does not need it any further. So if you see, in terms of the scope of the variable, anything allocated on the heap is not automatically deallocated when the function completes, like on the stack, and it does not need to live for the whole lifetime of the application like a global variable. We can control when to free anything on the heap, when to deallocate anything on the heap. If we wanted to store an array on the heap, like let's say we wanted to store an integer array, then all we do is make a call to the malloc asking for one block of memory equal to the total size of the array in bytes. So if we want an integer array of 20 elements, then we will make a call to malloc asking 20 into size of int, which will be 4 number of bytes. So what will happen now is that one big contiguous block of memory for 20 integers will be allocated on the heap, and we will get the starting address of this block. So we kind of get the base address of the array. This p will point here to the base address of this block, and then in our code we can use this 20 integers as p0, p1, p2 and so on. As we know, p0 is same as saying value at address p, and p1 is same as saying value at address p plus 1. This is what it means. One more thing, if malloc is not able to find any free block of memory, is not able to allocate some memory on the heap, it returns null. So for error handling we need to know this, and we need to write our code appropriately. Malloc and free, the use of malloc and free is C style code. If we want to write the same code, same logic in C++, then there is not much difference. Instead of using these two functions, malloc and free, we will use two operators, new and delete, and write our code something like this. So instead of using malloc, we are using the new operator here, and instead of using free, we are using delete here. If we want to allocate an array, we use something like this, where we put the size in brackets here, and if we want to free an array, we use this particular operator, delete and one bracket. With C++, we do not have to do all these typecastings, like malloc returns void and we need to typecast it back to integer pointer. New and delete operators are type safe. What it means is that they're used with a type and return pointers to a particular type only. So here p will get a pointer to integer only. We will be talking about dynamic memory allocation and other library functions in more detail in the coming lessons. So thanks for watching.